Does anyone still need the QR code? Okay.
So I guess we can.
Yeah, do you want to go ahead?
Do you want like put that also yes.
Okay. Do you want to introduce him?
Yeah. So I will briefly introduce our speaker, and then we'll go ahead and start the talk. So it's a great honor to have Bryan come here. So Bryan is a senior research scientist in GTRI, Georgia Tech Research Institute. He received his PhD in Louisiana State University. So it's quite surprising to see. I think Bryan has a mixture of hardware background, and he was doing a lot of algorithm research. Fortunately, he's also in my PhD thesis committee, so we do collaborate on a couple of projects, on one project actually, and it would be a lot of fun to hear his talk on what is quantum computing good for, and I think it's a good start for the semester. Let's begin the talk.
Okay, great. Thanks, Jack. All right, so as Jack was saying, I think this is the first talk of the group here, if that's right. And I don't know a whole lot about, what kind of things to expect for the rest of the semester, but I'm glad to talk about just kind of a high level overview of not necessarily something like an introduction to quantum computing, but, assume we have access to a quantum computer, what can we actually do with it? All right, the answer is not everything. It's only specific things that it's actually good for. And so I had a set of slides that we have presented to folks in the government, and I thought this fit pretty well with what I wanted to kind of cover. So we may not get through everything, and that's fine. If you have questions, feel free to just ask either during or after. There's no particular format. And through the course of this, I may just, by kind of use of the slides, give a rough idea of what GTRI is and what we do, but not in a formal sense, just kind of in a very brief sense. So this, as you can kind of see, this is really just a carryover from what we call a short course that we gave to some people in government. And sometimes this is things we do on occasion, in addition to doing specific project research. We also kind of try to inform elements of government on exactly what I'm going to be saying, right? So like what is quantum computing good for? Why do we care about a quantum computer, for instance? So it is fairly non-technical, right? Because we want people with non-technical backgrounds to actually be able to understand what it is we're talking about and why it's impactful, why it's important for them to care, right? Because there's still a lot of folks that know that a lot of people are interested in quantum computing, but there's not a whole lot of knowledge necessarily about why it's important, other than kind of the hype train, which we try to separate a little bit from the actual science. And so that's kind of the goal of some of this talk. So, one basic concept to kind of introduce is, right, we have kind of these two regimes for quantum computing, which is usually described as NISQ, which is noisy intermediate scale quantum, which is a weird term because, what do you mean by noisy? What does intermediate mean? There's a whole lot of kind of lingo that's not well defined. But it basically just means that the devices we have access to right now are all in this kind of regime. They're not perfect. They're, by a lot of regards, they're not very good at all. What can we do with them? Is there anything we can do with them? And that's kind of an unknown question still. And then there's kind of the far term, promise of quantum computing. And we usually refer to that as fault tolerant quantum computing for reasons I'll kind of allude to. But so we have these kind of separation of regimes for a lot of good reasons. And, there's a lot of hurdles from getting to one to the other. There's a lot of implications to kind of understand, why we have these two different regimes and what we have to do to get from one to the other. But then more targeted to what you would do with a quantum computer, right? Like what kind of algorithms would you run if you did have a quantum computer? So some of the highlight ones that most people are familiar with or would want to be familiar with are listed here. So it's things like a research algorithm, Shor's factoring algorithm, random circuits for quantum supremacy is something that was popular a few years ago and still sees attention from time to time. And right now in this NISQ era, we have these hybrid algorithms, which kind of usually are kind of part quantum, part classical, meaning they usually couple to some kind of classical optimization routine, but they still, run on actual quantum hardware. So I'll talk a little bit about those. And then we have also several, algorithms which kind of fall under this special purpose solver class, which are kind of a different flavor. And I'll talk a little bit about what those are. And so, still, we're still at a pretty high level. So if we think about, what are the industries that people typically think quantum computing can have an impactful result in? And it's not exact, but you can kind of classify them into several different industries. Something like, the tech industry, chemistry and pharma, finance, things like that are kind of the obvious ones. And then you can break those down further into like, what are the use cases within those industries that would actually look like a problem that a quantum computer would solve. And so you can kind of get an idea of what companies or industries may care about quantum computing based on the problems that it may solve, right? And this kind of gives you a scope of what types of, money impact it may have, right? And this is also fairly old already from this collection of data, but this is still kind of like what we're thinking of in terms of where quantum computing may actually help things and develop things and be better than a classical algorithm. And so listed on the far right are like these giant companies, right, that are involved in each of these industries. And most of these are, billion-dollar companies, right? So the basic idea is if you had a quantum computer that could run an algorithm that could solve a problem that these industries care about, it only really needs to be like a few percent better than the classical algorithm, right? Why? Because, right, a few percent of many $1 billion is still a lot of money. And so they really, really care about even just a few percent. That doesn't mean it's easy, right? A few percent doesn't seem like much, but classical algorithms have had a lot of development over a long time. So quantum algorithms still sometimes have a lot of leg to make up to kind of overcome the current standard. And so far, really none have, right? That's the stage we're at. So then you can say, okay, we talked a little bit about these two different regimes of quantum computing, but what does that timeline look like? And what are like the technical details of each of those kind of time periods? And then what is the rough dollar amount you could guess that industry may have on the economy? And so this is a rough timeline, right? Just like an order of magnitude guess about how these follow. So in the NISQ era, right, we're in the NISQ era now, and we may be in it for another 3 to 5 years, give or take. That could be plus or minus a handful of years as well. And usually the distinction to make between this era and the bigger era is the lack of error correction. And so they have this term error mitigation, which you can think of like a heuristic version of error correction. It's not really, but you can think of it that way. It is a way to try and beat back some of the errors we deal with on quantum computers, but it's not rigorous, right? They don't work very well. They aren't guaranteed to work really at all. Or they have resource costs that are very high. And so we're not really sure if error mitigation is really worthwhile yet, but it's what we have at the current scale. So if you can do it, you might as well. That's kind of the logic. It's still kind of unknown what that leads to, if anything useful. But then once we get to kind of the longer term, when we moved into an era about error correction, so that's a lot more rigorous, it's more mathematically provable, but what you can do with an algorithm that has access to error correction. And just very broadly, right, error correction is basically just the ability to correct defined errors in your computation as the computation is running. And so this is similar to error correction in classical computing. It's a little bit of a different flavor because we have to worry about things in quantum, but the same basic idea applies. It's just a little more complicated on the quantum side, but you still need it, right? Classical computers have tons and tons of errors all the time, and error correction is always running. It's something you don't really see in the background, but it's always there. And so we do need something like that on the quantum side as well. It's just very costly. That's why it's kind of in this other regime. And really, we're still making pretty small steps towards error correction. And then even further than that, right? Even if you can just demonstrate basic error correction, you still need something on the hardware side to do what we'll call modular architecture. Just meaning that even if you have a lot of qubits, a few hundred, a few thousand, you can't cram too many qubits on a single fabricated chip, for instance. You will need to hook these modules up together in some way, regardless of what architecture you're thinking about for quantum computing. And they have to talk to each other in terms of quantum channels. And that looks different for every architecture, but in principle, all of them have to do this at some scale. You can't just keep, putting more and more electronics on a single chip, for instance. And how that exactly is going to work is still pretty unknown. A lot of different people have different ideas about how to do that, but it's pretty crucial to the very long term on its actual impact. So this is kind of a rough plot about, thinking about different algorithms and what their applications may be in terms of, how long does it take to run these computations and what problem size do they correspond to? And again, these are very rough numbers, so don't worry too much about exactly where all the dots are, but it's just supposed to give you an idea of how many different problems scale and what is their time component for these different algorithms on quantum computers. And for some of them, it's quite favorable, right? Like you can go to very large sizes and the time scale does not increase very much. And that's really all you're looking for, right? You're looking for a problem which has a useful application and it scales well in terms of a quantum algorithm runtime. And there are several candidates that do that. But you can also get an idea that a lot of them also do tend to see the best kind of application at the larger scale in terms of size, right? Classical algorithms can kind of brute force small sizes, so we're not so interested in small size just because, right? Even poor scaling exponential time algorithms on classical, you can just kind of brute force small scale, and it's not very practical anyway. So we're really caring about things roughly about at least bigger than 50 qubits, for instance. And it's arguable whether even 50 is useful. But really, that's the regime we care about, and regimes larger than that. And you can kind of see in the legend here, I'm just trying to highlight that these problems do correspond to completely different industries in some cases, right? We have chemistry, material science, factoring, machine learning, industrial optimization type problems. And so those can apply to completely different industries. And they're just because of the fact that the algorithm itself, the type of problem it's solving corresponds to the different individual industries. But these are just the kind of current, well-known algorithms that people may care about, just to give you an idea of where the kind of hype is coming from. Well, it's going to solve everything. No, it's not going to solve everything, but there are certain well-known problems that it can solve quite efficiently. And that's what a lot of people are interested in. And you can kind of classify these into, what is the mathematical problem that they're trying to solve for these quantum algorithms. And for the most part, you can almost always put them in these different buckets. So it's like a combinatorial optimization problem, or it's some kind of differential equation, or it's a linear algebra-based problem, or it's a factoring problem. These are like most of the classes of mathematical problems that people have good algorithms for. And then, we also list, like what is the actual application for solving that. And so the distinction here is to make that realistically, there's only maybe a dozen or so useful quantum algorithms at the current scale. There's different flavors of a lot of them, but there's just really only, a handful, a dozen or so. But that's enough, right? That have guaranteed like better solutions than classical. We're not to the scale at which they're better, but you can prove that they're better in terms of scaling. And that's really all you need, again, like I said, the industries you have access to for these problems, again, you don't need that much better solution quality, you just need a little bit. And these are multi-billion-dollar industries. And so no one's really sure, what is the area that you may care about most. It varies across the economy. There are several, that are pretty important for different reasons. But kind of the idea is everyone's going to care about something slightly different depending on what they think the large impact is. And I'll talk a little bit about kind of where each of the highlights come from. So as a high level, without getting technical at all, why is quantum computing better than classical computing for some problems? And so this is not the correct analogy, but this is like the easiest one to explain without going into a lot of math. So if you think about, parallelism in classical computing, right? If you just want to run things in parallel, you're just, cramming a lot more cores to running the same copy of the same computation and kind of re-putting the result together at the end. So there's nothing really too crazy about that. So if you want to evaluate like some mathematical function, then you would just run it multiple times on multiple cores to calculate all the possible answers, right? Without having to run them in serial, for instance. But what does that look like on the quantum side? And so again, this is not exactly true, which I'll say on the next slide. But what you can think of it as is you could take all the inputs and run it once and get all the outputs. There's a caveat to that, which I'll mention, but that's roughly how you can compare it. So you get kind of the benefit of parallelism without actually needing multiple cores or multiple different CPUs or QPUs to do this problem. You don't need to evaluate all the inputs on different machines. You could just run it on one machine and it will sample all the results for you. And so the reason that's not true is because on the classical side, right, every time you have an input and you measure an output, that's a one-to-one correspondence. On the quantum side, you're still limited in that way, meaning even though the quantum computer does generate all the solutions, when you go to measure, you're only measuring one at a time. While in principle, they're all possible, right? It's probabilistic. And so you'll only sample one of the answers each time you run the computation. So you do have to sample from this distribution. In principle, you have access to it, right? But it's not simultaneously that you can just extract all the answers at once, for instance. So it's still just classical data that you're reading out from the machine, which you are kind of limited by the rules of quantum mechanics, which just says, it is probabilistic. So this is kind of the limitation of why that first analogy is not exactly true, but it's almost true. So if you want to, explain this to somebody who's not in a technical field, this is maybe kind of one of the reasons you would say where the power of quantum computing comes from. But it does have some limitations. So how do you get around those limitations? And that's what basically all the current quantum algorithms do, is they construct the algorithm in some clever way to get around those limitations. And what does that look like? So for something like Grover's search, which is typically an algorithm used to search an unstructured list, so you can think about like looking up, right, a specific item in a phone book, for instance. And so the classical approach is you just check, roughly half of the entries, and on average you'll find the answer or the entry you're looking for. But Grover's search says that you only actually need to check the square root of the number of entries and not just half. And right, so rough numbers, putting it to it, that's 1,000 versus 500,000 if you have a 1 million entry list. And so that's pretty significant, even though it's only a polynomial difference, right? Like roughly n versus square root of n is not a huge difference in terms of mathematical complexity, but it still can be meaningful in terms of hard numbers if you care about this type of problem. And a really rough way of what it's doing is it is checking every entry simultaneously because it generates these superpositions. But then you actually do have to do this amplification step, which is why you kind of get around the issue of you're only allowed to sample one answer at a time, which I mentioned on the last slide. And so again, this is just very high level, but just to give a flavor of like, why is Grover's algorithm interesting for anyone at all? And you can talk about it in terms of this complexity, this square root complexity, or you can just think of it in terms of that it is using superposition to try to basically use the basics of quantum mechanics to get a better result. But who actually can use Grove research, or like what industries or who would care about it? Well, in principle, if you think about an unstructured database, then almost everyone could use it. So if you're just optimizing something or searching something, but the kind of negative side is this, as I mentioned, it's a polynomial speedup, and that's not very exciting for a lot of industries, right? Typically, the best thing you could hope for is an exponential speedup. So something on the classical side that takes exponential time, and then on the quantum side takes linear time, for instance, would be one example of that. And then the algorithm itself is very costly. So one estimate from a company, IonQ, says you need something like 10 to the 27 number of gates, which is just ridiculous, in order to actually beat a classical computer on a practical problem using something like Grove research. So that's roughly like, if you plotted out what the classical algorithm does in terms of scaling versus the quantum algorithm, you would need to go to a regime that's so large that you need so many gates on the quantum side that it's just basically ridiculous at that scale. So there's just no like scaling regime where quantum looks really exciting for this particular problem. Nonetheless, it still gets some attention. So this is kind of like one of those pitfalls that's interesting from a pure theoretical standpoint. It is technically a proven speed up, but on the practical side, it's actually not that interesting because there is no like current or near-term possibility for this algorithm to be applied and show some, actual improvement over classical, for instance. So yeah, this is basically what I just mentioned. So in principle, Grover's algorithm is interesting from a purely like provable sense, right? You can show it does have a guaranteed advantage, but on the practical side, there's not a whole lot of meat there. And so that kind of leads into the question, how do you show that a real quantum computer is better than a classical computer for a particular task? And so usually that's just termed quantum supremacy, or sometimes called quantum advantage. That's kind of interchanged sometimes. But kind of the distinction there to make with this terminology is what you actually want to show is, a quantum computer is better than any classical computer for a useful task. So this is kind of the distinction in the definition. If you've heard the term quantum supremacy, that's a little bit more broad. It just means I solved some problem on a quantum computer better than a classical computer could. But the more useful question is, I want to solve a useful problem on a quantum computer better than a classical computer. And so that's still not been shown. So the first one being shown by several different hardwares over the last 5 years or so for mathematical based problems, which I'll talk a little bit about. But no one to date has kind of shown fully proven useful quantum advantage. And that's kind of the remaining next big milestone for the whole industry is what is a practical problem going to look like on a quantum computer? When are we going to get there? So then moving on to another algorithm based on factoring. So a real kind of snarky reminder, right? What are you doing when you're factoring for a given number, right? You're trying to factor into two whole numbers so that the product of those numbers give you your original number. And so how do you actually do this in terms of an algorithm? So just speaking mathematically, this is an NP problem, right? Meaning if you know the factors, it's easy to check that they're correct. But if you start from the composite number, it's not easy to find the factors itself. And I'll speak a bit about why this is important, but that's kind of just the complexity class that people typically refer to, which has useful implications, meaning, right, you can use that knowledge in your algorithm, meaning this guess and check. You just try a bunch of factors and you check them, right? And if checking them is easy, then you could just go through all the possibles and check them until you get the right answer. And so that's one approach, right, you could take. And you almost always use that fact in almost any algorithm, even on the quantum side. You're going to use the fact that you can check it easily to verify whether you're correct. And if you're not, you do it again. right? That's kind of built into almost all these attempted algorithms. And there's been a lot of different formulations of how to go about solving factoring problems. And kind of the most recent is this number field sieve approach, which is kind of the current state of the art. Basically, there's a lot of different changes that have been done to it, but this is the basic formulation since 1995, and it really only works for very large numbers, but that's the basic idea. So a bit more about why we care about factoring. So factoring is the basis for RSA encryption on a lot of cryptographic keys that are still currently in use in a lot of different industries. Internet, just general encryption is also RSA encrypted. And it's based on factoring, meaning it generates, your goal is to figure out the factors of some very large number. And because that's an NP problem, classical computers cannot do that efficiently. So it roughly takes it takes a long time for you to try to just kind of brute force crack RSA encryption because it's based on a known hard problem. That's the whole idea. So when Shor came up with this factoring algorithm for quantum computers, it was quite surprising and alarming, right, to several industries because of this fact. We have based our security on RSA for a long time. And the basic idea is like, if classical computers have gotten strong enough to crack a particular length RSA key, what do? You just increase the key length. And then now, classical computers have significantly more hard time breaking the new key because it's significantly stronger just by adding a few more digits, for instance. And then so kind of putting some numbers to this, if I took an RSA key and then I doubled the number of digits in that key, how much longer would it take a classical computer to factor that number? So on the classical side, it would take about 100,000 times longer just from that kind of exponential scaling that the algorithm actually has. And then on the quantum side, how much longer would that take? Well, it would only take about 8 times longer, right? So you could put numbers to that, right? If it took you a week on the quantum side, now it only takes you 8 weeks. Like that's not that significant, right? But 800,000 or 100,000 weeks is kind of a lot more, basically impervious in that sense, right? So this basically disrupted the whole premise of using RSA being kind of right, a secure method to encode data. And so actually NIST has just released kind of these post-quantum crypto standards for cryptographic keys, which I don't know a whole lot about exactly all of them yet, but it was just fairly recently. So they've defined kind of new ways to encrypt data to be resilient against quantum algorithms as well as classical algorithms. And so the only reason they did that is because of this existence of this algorithm, for instance. Right, if this was a proven standard that was right, like unbreakable, there would be no reason to redefine the standard, for instance. And so that has taken quite a long time for them to even settle on what is a new way to kind of encrypt data that's not based on factoring, because it's kind of a flawed system now, and at least it will be at some scale if we ever get there with quantum computers. And that's the worry, right? Is if even in I don't know, 10, 15 years, somebody comes up with a quantum computer and can run these algorithms at a scale that matters. Now, all of a sudden, they can break all these keys that were thought to be unbreakable. And data from 10, 15 years ago, which was encoded in RSA, whatever digit, is now breakable. That may still be pertinent data, who knows? But that's kind of a concern. It's just why this algorithm particularly gets quite a lot of attention from different governments and industries. And so this scaling is all just coming from the fact that roughly on the classical side, it scales like 2 to the b, where b is the number of digits in your key. But on the classical or on the quantum side, it's polynomial, so it's like roughly b cubed. And so these numbers are just coming from that fact, right? So if it doesn't really, I mean, once you take b to some regime, right, these separation between these two scalings becomes very, very significant. So you really can't rely on the fact that you can just make longer and longer keys and expect it to be much, much harder to break. So the basics of Shor's algorithm it is actually quite complicated on its own. I'm not going to talk too much about how it works, but it does have a kind of primitive inside of it called the quantum Fourier transform, which is used repeatedly within the algorithm to kind of amplify possible factors. But again, it's based on the same principle that almost all the algorithms are, is that it's actually checking kind of multiple factors at the same time and canceling out ones that are correct and then amplifying ones that it thinks are correct in kind of a repetitive fashion. So it can be quite complicated in terms of looking at a quantum circuit, lead to very deep algorithms, which is why this algorithm, along with many others, really only has application in the kind of far future fault-tolerant era of quantum computing. So where are we, with Shor's algorithm on current devices? Well, they've factored 15. We've done it. We figured out that 15 was 3 times 5 with current quantum computers. That's not super exciting, but that's where we are. There's been some other results, but they're kind of these one-off special cases that I'm not really considering. And in terms of scale, what are the devices we have? Well, we have quantum computers with anywhere from around 11 to 400 qubits. But what can we do with those qubits? Not a whole lot. Meaning, you can only run about 100 gates. Maybe that's a factor of 10 larger now since these slides were made. Maybe you can run 1,000 gates before you get an error that would basically disrupt your computation. And so that number changes a bit about what techniques you're using to try to mitigate errors, but we're just talking about rough order of magnitude here. And so that number needs to be much, much, much larger before you can actually run something like Shor's algorithm. And that's why we really only run, factoring 15 with this algorithm at this stage. And then, so to put numbers to this, to factor a generic n-bit number, so something like a 512-bit RSA key, you'd need 3 times n perfect qubits, so about 1,500, putting in the 512-bit version there, and then about 16 n cubed perfect gates, which is about 2 billion gates, right? So we're quite far from 2 billion gates at the current stage. And we would actually never get to 2 billion gates. That's why we need error correction. So the whole point is the gates themselves will be faulty, but error correction will go back and kind of correct errors on the fly as we run the algorithm. So in effect, we can, eventually get to 2 billion. That seems almost impossible, and there's lots of overhead with error correction that I'm not necessarily going to be talking about, but I think you might hear that in some other talks later this year. And so, who cares about Shor's factoring? Well, like I said, it's based on RSA, so basically hackers, right? If you want to break encryption, you care about factoring quite a lot, and so you can guess from there who cares about that. Almost everybody who wants to keep their data secure, right? It's basically the most important current quantum algorithm. Obviously, there's lots of other important ones, but this one has kind of the largest implications for a lot of different reasons. And it is an exponential speedup, right? It's that 2 to the b versus b cubed kind of scaling argument. And so it has kind of this provable improvement at a scale that people do care about, but it is still, in the far future that we could actually show something for it. And so this is kind of part of Shor's algorithm, but it's also an algorithm on its own, sometimes called quantum phase estimation, which in general terms solves an eigenvalue problem. So you have some unitary operating on some state equal to some other side with that same state. So it's just an eigenvalue problem. And what are the values of that theta that you want to solve for? So that's the mathematical description, but what does that actually look like in terms of problems that people may care about? So you can write eigenvalue problems for applications in industries like quantum chemistry, and also optimization problems. It's kind of a wide-reaching generic problem, right, to find eigenvalues of some unknown operator or some known operator. because it tells you a lot about the spectrum of what's going on, the dynamics that are generated by that. And so for quantum chemistry, for instance, right, it may tell you about how reactions happen in molecules, or when you're doing things with catalysts, right, that you'd actually don't want to do because it's either expensive or they're very rare and they're hard to create. You would like to simulate those and just know what the reactions or the presence of catalysts would do. And so those simulations are very expensive to do on classical computers, if not impossible, because finding eigenvalues is just a very costly thing to do classically. But so this is kind of the algorithm that would do that on the quantum side. But the drawback is again, it leads to very deep circuits. This is just kind of a rough showcase of what the algorithm looks like, which may not mean much, but I have not specified what all these gates mean and all these things. But the point is that you do need access to a lot of qubits, and you do need access to deep circuits, meaning relatively large or relatively small error tolerance to actually run this algorithm, similar-ish to Shor's. And this is actually a component of Shor's algorithm. So if you could run Shor's, you could also run this. So it's kind of a an inclusive statement. This problem itself may come before Shor's, for instance, but who knows? There may also be improvements to Shor's down the line. So I've talked a bit about error correction and fault tolerance. Why aren't we there? Or what is kind of the really high level description of error correction? And so if you have, so suppose a computer achieves 1,000 qubits and can run 1 billion gates, but it gets a fatal error every 100 gates, how can that be useful for anything? And the answer is, like I said, it's really not useful for anything until you can actually correct errors. And what does that look like on the classical side? As I kind of alluded to, right, we're already doing this on classical computers. All the computers running in the room right now are doing this error correcting constantly, right? There are constantly errors in memory that get corrected kind of automatically at this stage, right? It seems seamless from the user standpoint. But what's happening there is basically you can encode a single bit into a larger space, right? You could just copy a bit multiple times, and then if one of the copied bits suffers an error, you could just do something like a majority vote and know that all the rest of the bits are correct, and you should fix that one bit that got flipped incorrectly. And so that gives you some resilience to individual errors, right? Or some number of errors, depending on how many copy bits you use. And in this example, it would cost you 5, right? You have an increased space of 5 in order to get this error resilience. And so what do you do on the quantum side? Well, it's not exactly that straightforward to describe, so I'm not going to go too much into depth, but the same basic idea applies. You're going to need to do something to encode the zero quantum state into a larger space that is now resilient to errors. You can't just copy it like you do on the classical side, and you can't just do majority voting to correct it anymore. Things get more complicated because you have to worry about different kinds of errors on the quantum side. But the other thing to also care about is that the cost also goes up quite large. So instead of just a cost of 5, for instance, now you have a cost of about 1,000, roughly, right? Order of magnitude. There's a lot of caveats and conditions based on the way in which you're doing the error correcting and all these things. But the point to get across is that things become quite expensive to do error correcting on quantum computers, but it is theoretically proven that you can in principle do this and obey all the laws you need to in quantum mechanics, and it does work. But the overhead cost is just significant. And so that's what's kind of limiting us from just immediately realizing this regime on quantum hardware, for instance. Okay, so I talked a bit about these different regimes and just kind of highlighted what we need to get to error tolerance. But this also kind of implies that there's this segment between the two regimes for NISQ and fault tolerance. And so sometimes you may hear the term quantum winter, and this is this weird kind of term that people in the industry have coined, which basically represents, what if we lose interest in NISQ and never find anything useful in NISQ, and then we never get to fault tolerance, right? Because of this overhead cost. So remember that the overhead for just doing error correction is roughly 1,000 times, meaning at some regime, if NISQ isn't useful in generating money, how do you build a device that's 1,000 times bigger than that device if you've got no money? And so that's kind of the real concern of Quantum Winner. And it depends on who you ask. Maybe we've already passed Quantum Winner. Maybe we haven't even started. Who knows? But it's just the separation of kind of between the NISQ and the fault tolerant era. Is there going to be anything to carry the industry between the two? And it's up to who you ask on whether that's going to be a significant concern or not. And so the SID halfway mark, I don't know if it's actually halfway. I think a little past halfway on time. So I'm going to skip this and then briefly talk about the NISQ era and what it means on the current quantum computers. What are we doing with them, and what does the stage look like? And so again, we're at an era which we roughly have access to hundreds of qubits, but we have fatal errors roughly every 100 gates or 1,000 gates, something like that. So how do you do something useful with these computers? And so the only real option you have is to do very short computations so that you don't eat up too many gates in this kind of reserve. And then you keep repeating until you get an answer that's better than noise. It's kind of the strategy everybody has taken so far. And so, if you were constructing this quantum supremacy checklist and you wanted to generate a problem that quantum computers could solve better than classical, what would you do? Well, you would first make up a problem that quantum computers are good at solving, which is cheating, right? You knew the answer, so you constructed the problem so that you would get the right answer, which is not necessarily anything wrong with that, but that is the stage that we're at. And so these kind of quantum supremacy results that came from Google and some other industries also, photonics has also done them, and I think Rydberg Systems may have also done them. Basically, you're constructing a set of random circuits and then trying to predict the result of those random circuits. And roughly, that's classically hard to do just because you're trying to simulate a quantum system, which is kind of very costly on classical systems. And then you also randomize, which of the sets of circuits you're trying to use. And so you can't actually predict the answer very well on classical computers. There's a lot of tricks you can play, and people have kind of refuted some of the previously supremacy claims, but it's kind of lost to the details. It doesn't actually really matter because these kind of random circuit problems are not a practical problem, right? They're not going to necessarily make any industry more money. They're just a mathematical construction that is strictly true and strictly solves better on a quantum computer. So while they're interesting from like a kind of theoretical standpoint and provable standpoint, they're not super exciting if you care about solving problems that people actually want to see solved on real problems. And so this made like the cover of Nature, for instance, and is a very important result for kind of anyone in quantum computing. And what's the basic comparison here, right? You're comparing a quantum system to roughly the world's largest and strongest supercomputer, something like Summit or Frontier at Oak Ridge, for instance. This is a picture of, on the left, of Google's Sycamore chip, and John Martinez, who's not part of Google anymore, is actually starting up his own company now. I forget the name of it, but anyway. And the result is basically saying they constructed this random circuit result that could not be predicted by kind of the best of the best classical, which was again kind of refuted later by different improvements on the classical side. It's basically the idea is it's a moving goalpost, right? Like whatever you say the best classical algorithm is today, somebody will find a better one tomorrow. So they will tell you that the thing you did last week was wrong. But the point is the scaling is always going to be favoring quantum in terms of if you construct a problem that is favorable to quantum, you can basically always find a regime where it will beat a classical algorithm. You may just need to run to slightly larger qubit numbers, for instance. And so who can actually use a problem like this? Like really only academics, right? It's just kind of a thing that looks nice and it has implications in terms of press releases and things. It's interesting from a theory standpoint, but we still really need to get a regime where we're doing useful problems. So it's very important in terms of fundamental science, right? Like if you're trying to prove some universal law, like this is in that regime, like it's very important from a fundamental standpoint. And it may have some application in randomness, like you can maybe turn these supremacy circuits into pure randomness generation, for instance, but it's kind of still up in the air. So I talked a little bit about error mitigation, but what is the rough idea of that? But basically it comes down to, there are certain techniques you can use to try and improve the error rates of current machines. And some of them work fairly well, and some of them don't always work fairly well. And they're kind of just all over the place. So that's why I kind of attribute them to something like heuristics, right? They're not guaranteed to always work well, but there are cases where they do work very well. And you have to know a lot about the hardware that you're using and how you're configuring these things. And so it's not to say that they're not always useful or they are always useful. There's a mixed bag for kind of all of them. And a lot of them are not scalable. That's one of the main drawbacks is unless you can make certain guarantees about how they scale, then generally they don't scale favorably, meaning you cannot always run them on any size problem just because the time it would take to actually run them would kill any potential improvement. Like maybe it will improve your result by 10%, but it takes you 100 times longer to run it, for instance, right? And is that even fair to do? Maybe not, right? If it's like a post-selection thing only, then who knows whether that's actually something you could claim is better or not. But generally, they also require, some sort of classical post-processing, which is why, I'm saying they sometimes can take a long time, and additional experiments, meaning you need to actually run the quantum computer a lot of extra times to extract the information you need to reconstruct these mitigated results. And so they're kind of just something to be taken with a bit of caution at the current scale. They do have their place, but they are not a tool that always works and always gives a reasonable answer and kind of can always improve something that you're doing. And so kind of an example of, I mentioned some MP problems, what does that look like on the practical side? And so one example, there's many others, is something like a traveling salesman problem where you're trying to find a route to visit a certain number of locations and each only once, for instance. What is the route that is optimal in terms of like minimum, overlapping, not having to go back and retrace your steps, things like that. And so it is an NP problem, meaning it's hard to solve classically. There are algorithms that do it, right? This little animated GIF. There's I think simulated annealing algorithm that's running and trying to solve this traveling salesman problem on this number of nodes. And so of course it is doable, right? But it's just the argument is the scaling of the problem is not very good. And it is thought that maybe the scaling is a bit better on the quantum side. Something like, traveling salesman, you might have a better result, but you're not guaranteed to always get a better result for all NP problems. So you may get some improvement for something like Grover's, but again, it's not to the level that you may want out of an improvement. And there may be a lot of special cases, right? You could construct a problem that has a certain type of structure that maybe the quantum algorithm is very good at, but then the question remains, is that actually useful for anyone to care about? Because it has a very fixed structure that you just kind of made up. So what we really want is to find a general improvement, right? Like I have an algorithm that can improve and solve all these problems better. That's actually really hard to find. So I may skip some of this a bit because I know I'm getting close to time and I want to leave at least some time for questions or discussion. And so maybe I'll just, so QAOA and VQE, I'm going to go by and kind of combine because they're similar in the sense that they are these eigenvalue problems that I mentioned before. So they aren't using the quantum phase estimation algorithm to solve, but they're of that same type, meaning they are solving an eigenvalue problem, but in a different way. So QAOA and VQE are these kind of hybrid quantum classical algorithms that generally have both a quantum portion and a classical portion. And the classical portion runs classical optimization to try to update parameters in the quantum circuit. But they have some problems because of that fact that they're relying on these classical optimization routines. Speed is one, how many iterations do you need to run before you converge? That's generally unknown. And then the optimization also has issues, right? Like any optimization routine does. You're not guaranteed to converge to a global optimum. You could get stuck in some kind of barren plateau and never converge, right? That's no different on the quantum side. And so relying on these optimizations is sometimes squirrely. And I won't go into too much of the details of that, but that's kind of the high level version. And you can actually adapt VQE to solve things like linear PDEs. They're not actually that much different. It's just, again, you turn it into an eigenvalue problem and you solve the eigenvalue problem. And now you've solved your original PDE as well, but it has the same concerns. So you're not guaranteed convergence, for instance. But even just considering linear PDEs, you have quite a lot of different mathematical problems that fall into that class. And these are just kind of a rough sketch of like all the different types of practical problems you may care about that fall into this class. So briefly then, special purpose algorithms, what does that mean and what do they look like? And so all I really mean by special purpose is you're not constructing a generic algorithm, you're running something closer to, you can think of like any software you have on your computer that can solve specific problems, right? It's not something like Mathematica that you can just type in equations and ask it to solve, but it's something like special purpose solver. It really only solves one type of problem, but it does it very well, or it's supposed to do it very well. And so that's what things like DWAVE are, just to give some contrast. So it can solve optimization type problems, and it may do them pretty well, who knows? The jury's still kind of out on that. But it really is not a generic quantum device, it's a special purpose quantum device. Like you have to give it a problem that it is capable of solving. You cannot just map generic problems to the device. And there are several others in the quantum communities currently which fall in that class. So that's just to give an idea of like what the difference between kind of a general purpose quantum hardware and a special purpose quantum solver. This is another example for boson samplers. And so they're based on optical frameworks that sample from photon states kind of being shuffled through a large number of beam splitters, for instance, and you can construct problems out of these, but again, they're not generic, right? You cannot map an arbitrary problem to a boson sampler. Nonetheless, they can be used for certain special problems, but again, it's kind of a narrow focus. So it's something in contrast to the more general quantum computing platforms. And then similarly, you have these Rydberg systems, which can solve problems like maximum independent set, but that's just because it very closely matches what actually happens on the physics of these Rydberg systems. And again, there are some versions that can be universal into generic problems, but there also are versions which are only special purpose. They cannot be fully programmed. And so they're kind of in this weird dual regime where it kind of is and kind of isn't, depending on which system you're talking about and what stage of development they're at. And this was just kind of a high level perspective of all the different architectures that we're currently at with quantum computing, what they mean in terms of how the qubits are physically connected, and all the advantages, disadvantages, and how you actually get access to them. So I won't read through them, but this is kind of just to give an idea of each architecture is physically different. The physics is pretty different on a lot of them, but when you get down to it, you have to define a qubit, you have to define a set of gates, and then you have to define how you do operations on them and read them out. Those are all the basics between all of them, but they have a lot of different implications across all the different industries. And who knows, what you consider to be the best. There is no real best, I guess. It's hard to nail down. And this is roughly, I think, the last slide, so I'll just pause here for any questions or comments.
Thank you. Does anyone have a question that they want to ask? I can start off with one. So you talked about error correction and how the goal is to get to some, like third stage in the future where we're using modular architectures for quantum computers. And there's a lot of people who argue, like for companies that are like Alice and Bob and Oxford Ionics that are saying, we're not even going to try doing error correction. We're just going to have systems that are perfect enough, let's say, to run useful quantum algorithms. Do you think that's a reasonable approach, or do you think quantum error correction is still a necessity?
So I think it will always be a necessity. So I've seen a bit about companies like Alice and Bob, and I'm not sure what they're trying to do exactly, right? Because they're creating these cat qubits, which are very resilient to one type of quantum noise, but they're like exponentially sensitive to the other type of quantum noise. So it's weird that they would say something like that, because even they need some sort of resilience to noise, right? Like in principle, you can run classical codes with their system because it's so resilient to bit flips, for instance, and that they could run extremely large what's called repetition codes, which is a classical code. But it's not good enough, right? That doesn't actually do a whole lot in terms of quantum errors. So your computation would actually still be junk at the end because you're ignoring all the other types of phase errors. And so I get the impression that they're a company that is trying to market themselves in a particular way that's not completely true for most of the field, unfortunately. Oxford Ionics, right, is a smaller ion trap company, and I mean, as far as I know, they are still also doing, well, it's not also, but they are doing universal quantum computing. So while they may have very good qubits, they still have noise to contend with, like anyone else, and so they will eventually enter a regime where they have to think about error correction. It's not to say they won't have anything useful in the NISQ regimes. Somebody probably will at some point, who knows, but it will be limited, right? It will not be, we can solve every single problem with our NISQ device. It would be, maybe we can solve this one problem and it will solve it a little bit better or something like that. But I don't expect it to be, world changing, for instance.
Thank you.
Hi, I also had a question about the differences on the slide before this between certain quantum computers. You talked about how the disadvantage of some photonic than any other computers are based on the fact that they're not universal. Could you talk more about like why that distinction between not universal and small measurements matters for certain experiments or algorithms that might be useful for to run with quantum computers?
Yeah, so usually when people think about formulating a quantum algorithm, they start with a model of universal quantum computing, and all that really means that it can't be a special purpose solver. It has to be able to do arbitrary qubit operations, and these non-universal architectures are not capable of that. They have very specific controls. They don't speak in terms of like, I want to rotate this qubit by this amount at this time. They talk more about things like, I want to change my experimental parameter, like I want to change the time-dependent tuning field of my lasers at this rate or something like that, which is just kind of a different limitation, right? Like, I'm trying to think of a better example. It's maybe something like, so if you would compare like a car to a train, for instance, right? In principle, a car can drive anywhere. Maybe you say it should drive on roads, but in principle, it could go wherever there's enough space for it, right? But if you think about trains, right, they're kind of limited to the rails itself. They have to follow within their own controls. It does not have kind of this freedom to do whatever you want it to do. And that's kind of the rough analogy I would make, is that these non-universal architectures still, right, trains have a very real purpose. They can do certain things very well, right? But they cannot do everything a car can do, for instance. And there are certain things cars are better for. And that's the rough analogy I would say, is that there might still be use out of these special purpose solvers. They have advantages, but they're just not as free, right? They're not as free to solve everything you want to solve, but they may solve very specific problems pretty well.
Any other questions? One last question I might ask if no one else has any. What advice would you give for someone who's interested in starting to, learn about quantum algorithms and maybe even do research in them? Like, do you recommend that they learn more physics or math or computer science, or what would you say?
So it's kind of it is a necessary evil of the field. Well, first it depends on whether you're interested in the theory or the experiment, right? And that kind of sets one path at least. There's a lot of different experiments going on with the different hardwares. There's some transferable skills. There's not all of them, right? So certain technologies use different devices to different amounts. In terms of background theory or something, they share quite a bit of background theory, which is pretty transferable between across the different architectures. So that's one thing to consider. In terms of kind of other skill sets on the theory side, and even a little bit on the experiment side, you do have to have some ability to code up, right? Simulations or even code up control software. Classical computers are always going to be a component of quantum computers in some way, right? We're always going to control quantum computers with classical computers to some degree. And so there's always going to be room for things to do with, coding on classical computers, or even just running quantum simulations and understanding how those work. Probably the easiest starting point, right, is there's tons of open source quantum simulation software now, and the biggest one being IBM's Qiskit, which has tons of good documentation for learning all these things, even some basic algorithms, not necessarily the ones I talked about here, but some of the more NISQ friendly ones, but they have a lot of good material. So if you're starting from scratch, that's generally the place I start.
Okay, thank you. Any other questions?
I had a question.
Yeah.
Are there any internship or research opportunities at GTRI currently, or as beginners, where could we look for those opportunities?
Yeah, good. So the kind of stipulation for GTRI is generically we are only able to have interns or hire students through kind of collaborate with campus that are also termed US people, and so that's kind of the biggest hurdle for us, and we have no negotiation for that. Other than that, there's a lot of opportunities that we run for student programs. I forget the names of all of them, but we have like 3 or 4 different student kind of interfacing ways that we hire on student interns. And we actually have, I have to plug this just because there are people that are using it in our group, but we have, researchers or considered faculty on our team that are also students at Georgia Tech. And so they're kind of co-doing both their, PhD program while working. And so they have to do both full time, which is hard, but they also, have their degree paid for. So that's kind of the benefit there. There's a lot of programs, different organizations that do that, but we are also one that does that, and we pair with campus. Beyond just us, there are, other places to get internships in this field. I'm not going to say they're necessarily easy to get into, but I don't have any specific sources to point you to, but I do know that there are other organizations that look for people learning quantum computing and want to do internships.
Any last questions? If not, thank you, Brian. We really enjoyed your talk. It was definitely a good introduction for the semester, learning everything about quantum computing really briefly. And yeah, Jack, do you have anything else?
No, I guess, if you're more interested in opportunities in GTRI, is that okay? Like some students email you, Brian, like later, just follow up like, summer research or anything like that.
Yeah, that would be fine. I mean, chances are I would point them to kind of our student coordinator, but it's also fine to email me, and I can interface you with with Rob Clark, who kind of handles all of our student interaction.
Yeah, okay, thank you. Yeah, as Bryan said, you know, if you're interested in those opportunities, feel free to contact him for further information. And thank you, Bryan, for the great talk. Yeah, thank you. And I might follow up with you about like, because we're setting up a YouTube channel and a website something, and for those like copyright things, we can, I can follow up with you later.
Sure.
Yeah, let's thanks the speaker again. Thank you.
Bye.
Thanks. Bye-bye.